Morning, Steve. Well, again, we have this prominent lineup of speakers. Our first speaker is Professor Abdelfattah Seyam. He is Professor at the College of Textiles, North Carolina State University, where he's been since 1991. Originally, bachelor's and master's degrees from textile engineering at Alexandria, and PhD in fibre and polymer science from MC State University. Over 60 publications on fabric formation. Number of patents and patent disclosures, software packages. Professor Seyam is going to speak to us about weaving technology, advances and challenges.
Assalamu alaikum. Good morning, everyone. Today I have a message, very significant message for weavers. So weavers, watch out what I'm saying, because you need to get ready for competitiveness from other technologies. When the organizers contacted me and invited me to do a lecture in a plenary session, I decided to take these topics and present it here today because I know Egypt is one of the countries where weaving is very important. So what I would like to do first, I'm going to talk about advances in weaving. And these advances happened during the last 12 years or 10 years. And if you have been in the shows, machinery shows at ITMA and ACME in the US and in Europe, you will be really surprised by the advances that took place during the last 10 years. Among these advances, we have seen higher speeds in weaving than before, more automation all the time, and we have seen new jacquard concept that is going to make the weaving industry revolutionary, and it may be the hope for the industry to survive the competition that's coming from other technologies. Talking about speeds, we used to see the 2000 rate of filling insertion. We used to have 2000 as a barrier. This barrier was broken in 95 and 99 at ITMA. And I'm showing you here many of these companies, top weaving machine producers, break this barrier. You can see that we have reached over 3,000 rate of filling insertion. This is the amount of filling yarn that's consumed in 1 minute. That's indication of the production. It's independent of the weaving width. So you look at this number, and when this number is getting higher, you know that you are producing more fabric. This is about speeds. That was air jet. Water jet, we have more than 2,000 by two companies. If you talk about repair, the 1200 and 1300 was a barrier. Barrier was broken. Higher speed. And then we have seen a revolutionary technology in weaving that took the speed from 2000 to 6000. That's what you see here. Multi-phase weaving is using multi-shades. So you are doing 4 in this technology here, developed by Sulzer. You're doing by air jet 4 pigs at the same time. which increase the production about 3 times as compared to single phase, which I showed you prior to this slide. And this technology is, if you look at it, new principle in weaving. You have here, instead of the traditional reciprocating motion to form the shed, you have a rotating motion to form sheds on a weaving rotor. And the rotor, around the rotor, will have 4 sheds that's ready to accept filling yarn. And continuous insertion on the 4 sheds is done through an intelligent way of forming a shed, using guides, warp guides, to raise the warp or miss the guide to put the warp yarn down. And you can see here we have 1, 2, 3, 4 sheds, and you have a slot on every guide that will allow the filling yarn to be released during weaving at the B-top. This is a real machine, and here are the shades. You can see number 2 and number 3 in this picture here, but like I said, they are 4. This here is showing you in red across the machine. You have 4 filling yarns inserted at the same time, and they are quarter revolutions out of phase. For example, this peak here made it all the way. This peak here, 3/4 of the way. This is half the way, and this is 25% of the way. And this is happening simultaneously. All the time, when you picture this machine at any moment, you would see 4 peaks inserted simultaneously. This is another view for the same thing. And this is the way they beat up in this technology. They beat up by fingers, very thin fingers. You see here, this warp yarn was lifted from the tunnel. The filling yarn was lifted from the tunnel by the warp yarns. And then you can see how the beat up is performed. If you look at this picture, you can see how we beat up the filling yarn with the fabric. This technology appeared in '95, and they showed it to run at about 6,000 rate of filling insertion. Using the rotating motion, it is expected to be more than that. From 95 to 99, they were able to increase the speed a little bit. But I'm predicting this technology, if developed more and more, you can probably take the speed 4 times, at least 4 times as fast as any single phase air jet weaving. So it can go to 8,000 easily in the future. 8,000 meters per minute filling insertion rate. I believe this technology will enable the developing country to compete with the developed country to compete with developing countries. And you can see that 3 countries already have this machine. 3 countries, 2 countries in Europe and 1 plant in America are using this machine and trying in production line to produce commodity fabric. The limitation of this technology, it just use simple weaves. It can produce simple weaves. What they do now is plain weave and 2x1 twill. And if you look at the design of the machine, you can see this is not going to be any better than that. It's going to be limited to simple weaves. And this makes the machine limited to commodity fabrics. High speed production for commodity fabrics. Looking at jacquard. 2 machine manufacturers produced a new jacquard concept. And by that concept, they were able to put the jacquard machine right on the machine, just like any derby mechanism. Instead of building gantry to put the jacquard head on top, you just merely need to put it on the frame of the loom. And in this way, they designed it so that you can reduce the machine parts, so the machine can be faster. And also they elected to to have every warp yarn controlled individually. So every single warp yarn is controlled by a hook or equivalent to a hook that we used to have or to know traditionally in the weaving industry. And here is some pictures. This is a crosser. You can see the jacquard head right on the top of the loom. And here is stopping. Unival 100, this is the name of the machine. And in here, this cord here is over 7,000 cord. Every cord is controlling one warp yarn. And every cord here, harness cord, is driven by a motor, stepping motor. So this machine has 7,000 little stepping motors that are controlling the shed opening of the jacquard machine. That's another view from the top. You can see that the jacquard head is on the top, right on the top of the frame. And here is a traditional jacquard. You can see how high you need to put the jacquard because of this slope here. If you don't have the jacquard head as high as this, you will get unclear shed. That's why you have to raise it up. Versatility was taken care of in the last 10 years, 12 years. So Dornay was presented this in 95 and 99, and 99, Dornay was the only one to present this. But in 95, many of the machine manufacturers showed quick style change. And quick style change, they changed the entire style in 30 minutes. 30 minutes, that's all what you need. And this will set up, if you acquire such technology, it sets you up for short runs. You can switch from style to style in no time, 30 minutes. Traditionally, or if you don't have quick style change, you need probably 5 hours to one shift to change the style. Automatic pattern change. In mechanical jacquard, we used to stop the machine for 20 minutes to change a pattern cards. And then came electronic jacquard. Electronic jacquard allow you to take the design from the CAD system on floppy, say, and then load it to the UCP units of the machine, which is a computer. And then in 2 minutes, you are ready to run new styles. Now, even this 2 minutes has been eliminated. You can program your computer so that the pattern can change automatically without no stop, not a fraction of a second. You can change from pattern right away. The pneumatic tuck-in is normally done by needles, mechanical. We have pneumatic tuck-in now in about 3-4 companies doing pneumatic, so that you can speed the machine at air jet speed. If you have air or air jet loom, you can use this. And instead of putting needle to slow down the machine, you have air which is faster than the needle, the mechanical parts. And this allowed the air jet to enter to a new market that it was not competing before. So air jet looks like everything is going air jet. You can put electronic jacquard on air jet. You can weave multi-phase weaving on air jet. So keep this in mind for the moment. Variable peak density is now available in the market. A machine that can make the take-up and let-off variable. So you can weave thick parts or heavy parts and light parts on your weaving. We used to have this in vertical direction by doing different denting. Now we can do it in the horizontal direction, so we can get fancy effects. All this versatility are at your hand now. If you can invest, you can get it very easy. Start market prevention This is quality problem. If you leave your loom for a few minutes and start it will have start mark, or what we call sometimes stop mark. It could be heavy mark or light mark, and this is a major quality problem. If you are in the business, this is 4 points. This is the highest number of points that you give your fabric quality. We range it from 1 to 4. The defect could be 1 or 4, or 1 to 4. So this is major, and if you have 4 of these in 100 meter, your role is second quality automatically. So machine manufacturer paid attention for start mark prevention, and it has been improved over the years, but it still needs the operator intervention when you have new style. Once the operator adjusted the machine and his vision looked at no defect, the computer remembers what the operator done, and once the style is running again, the start mark will be prevented. On normal inspection, this is happening, but it's sort of expensive. I don't see this is going to take place and spread unless you have very high quality fabric and you have the market and it's paid for. This system this vision system can see the defect and can stop the loom or flag the loom which has a problem, so the operator can come and fix it. We can also introduce the so-called sumo motor. Sumo is this wrestling sport where it needs powerful people, as you know. So they call the motor sumo for its power. You can connect this the motor connected to gears. There is no pulleys, there is no slippage. So you can transfer the power of the motor directly to the machine parts. So you get the beat-up force, same beat-up force quickly for the first pick. So some of the start marks can be prevented by using such technology. We still need they put this also in airjet. They showed it on repeat, and now it's going to airjet. This also will allow you to change the speed at any moment. And this will allow you to have different filling yards. Say you have a filling yard that can run at 1500 pick, but another filling yard you need to use to get fancy effect that can run at only 1000. So instead of slowing your machine to 1000, that sumo motor can change the speed from 2000 or 1500 to 1000 very quickly and to adapt to the filling yard which is weak. So you can put a variety of filling yards, but different quality of filling yard can be handled with such a machine without using the speed or the better quality filling yard. Now, is this enough? There's no doubt that we have advances in weaving, but what is the speed of a weaving machine? How many square meters per hour that we produce in weaving? About 40 meters square per hour, right? With all these advances, we're still very slow compared to technologies that I'm going to present to you now. We have weavers. I'm a weaver, and many of you know me. We were classmates, or I was instructor. You've seen me as an instructor, and some of you are friends. We met during many occasions that when I came to Egypt and so on. Egypt depends on weaving. Now I would like to show you here two technologies that I believe they are very tough competitors, and they're going to take a lot out of weaving in the near future. They've taken already some, and they're coming strongly at the weaving to take more. So watch out. Needle punching and hydro tagging. What's needle punching? I'm going to skip here and show you simply what's needle punching. Needle punching is technology where you feed fiber web, no yarns. You just get from a bale of cotton or polyester or mixture of anything This technology is not picky. It can handle any type of fiber. Short, long, polyester, synthetic, whatever you put there is going to be processed. And what you see here is only the part where you entangle the fibers together to form the fabric. Derived in this part here, you have an opening line and carding line and cross-lap line to form a fiber mat with the weight and thickness you're looking for. And you bring this by the feed mechanism to the needling zone where you receive, the web receives high-speed needles. You have needles here that goes up and down, needle board goes up and down, and every needle got several hooks, or what we call barbs. These barbs will take the fibers from the surface, push it through the thickness, and you get the entanglement and the integrity of the structure you're looking for. You can change, of course, needle intensity depending on the end use that you're going to put your fabric on. Needle punch line can also have finishing parts at the end here, so you get finished fabric. So from bale of cotton or polyester or whatever, you get finished fabric. You start from bale and you get finished fabric. In '95, Fibre introduced a patterning. They can do patterning. After you entangle your fiber web, you have so-called special needles called structure needle or fork needles. If you feed two colors to this needle and you have the needles arranged in a certain way, you could produce such fancy effects. How many colors you see per in any instance here? Two colors, right? It can handle two colors so far. And this is very challenging for the carpet weaving. We can do carpet here. What is the speed of needle punching? I have run here some calculation on the speed of needle punching. Depending on the needle intensity and depending on if you have single board or double board. You can put double board. Let's say we have double board. And let's say we have here highest needle intensity on this curve. It's 100 meters square per what? Per minute. 40 for weaving, 40 meters square per minute. This is 100 meters square per minute. In weaving per hour, 40 per hour. So do your math and see the difference. I was showing here, I skipped this part here. This is the end uses of needle punching. And these end uses used to be dominated by weaving before needle punching appeared to the scene. They go everywhere from agriculture, all technical textiles, and I can add to this list carpeting. It's there already, but you can add carpeting, and it's going to steal a lot from the weaving industry. Hydro-entanglement. Hydro-entanglement is very similar to needle punching. Instead of using needles made of metal, you use needles made of water. High pressure water comes to the web and hit the web at very high energy, and this will make the fabric, form the fabric integrity, entangle fibers together. Whoever thought about hydro-entanglement process, he had in mind that we need to produce a fabric, just exactly look like woven fabric or knitted fabric, but done with a non-woven technology at the price of non-woven technology. Very cheap price compared to woven. Here is the principle of entanglement, or principle of copying the shape of what you see at the end of the process. We have here water jets coming, and you will have holes, the jets, arranged side by side. So when you see 8 meter machine, for example, you will see jets coming out of holes that's wide width of 8 meters. This is an unwoven web on the top here. On the bottom, you have what we call the forming surface or forming belt. That belt is made of wires, and say it's woven. So this is woven fabric, like woven fabric, but it's wire. When you hit with high energy water the web, the fiber will be displaced around these wires. And you will see exactly that you copied the wire or the forming belt. So your fabric will copy the exact shape. It will be negative copy, but if you have plain weave, negative and positive are the same, so you copy, you get plain weave appearance. And here it is. You have here woven fabric on the right, and you have hydro-tangled fabric on the left. So we can copy that and get the same appearance. This picture taken by one of our students. He's working on hydro-entanglement, and you can see here by adding pressure to the gauge, at low pressure you get hazy shape. You don't get the structure developed right. Until you find the right pressure and right energy, you can get the shape you're looking for. If you exceed that, you get, again, displace the fibers where you don't want them. I don't want to really elongate this more than that. How many minutes we have, Mr. Sheldon? 5 minutes, so I feel it. What I would like you to take from this here is this technology is growing about 20% every year, and it's taking from woven and knitted markets. This shows you here the distribution of the markets for such technology. We call it spun lace or hydro-entanglement, it's the same. So you can see here. Look at this part here, industrial apparel. We have industrial apparel, it's multi-use. Recently, they developed items or articles for apparel that you wear every day. And Mr. Ken, can you show the audience the pants that's made of hydro-entanglement? And if any weaver comes to look at this fabric or to look at this pant, and I will ask you what weave is this? Many of you, I already met people and they said, yeah, this is woven fabric, woven fabric. Is that close? This is another technology doing the same thing, but instead of starting from bale, they start from the polymer chip. So this is more integrated process. The spinning is included there. And this is continuous. The hydro-entanglement is using short fibers, and it can use actually continuous fiber. But the heavy long process developed by Freudenberg uses polymer chip, and from polymer you can get finished fabric at the end of the line. Now the question is, what is the speed of this hydro-entanglement? It's double the speed of needle punching. So we're talking about 200 meters square per minute. Double the speed of needle punching, and you can estimate how much faster than weaving. How weavers can face the challenge. Hydro-entanglement or needle punching, like I said, the limitation there would be the two colors, right, in case of needle punching, and limitation would be, in case of hydro-entanglement, would be commodity fabrics. It's going to take a lot from weaving industry in the coming years, 5 years, 10 years from now. We'll see a lot taken from the weaving industry in the commodity fabric area. They can also do designs, because non-woven industry is always doing R&D. You can find the ratio of personnel in R&D much, much higher than any other industry. You can see also the patents coming out of the non-woven industry, tremendous amount coming out of them. So they keep thinking all the time, developing all the time. In the 70s, who can imagine that the waste industry turn around and becomes very competitive to the weaving industry. When we worked on a project in 1972, the non-movement, we were producing very stiff non-movement. And one of my colleagues sitting here, he was working with me on that project. We worked together, doing non-movements, chemically bonded non-movements. That's what we know at that time about non-movement. Today, 30 years later, it is completely different. It's coming strong, and it's going to take part. What you need to do as a weaver, you need to look at the limitation of these technologies, and you can do better. Today, you can weave on air jet weaving, the fastest weaving. You can weave jacquard fabric in the case of single phase. Can the machine producer give me multi-phase that can I put on jacquard? Not yet, but this is a challenge. We need to do it. Short runs, they cannot compete with you in short runs. They cannot compete with you in very lightweight. For the moment, for probably 5-10 years from now, like I said, you're thinking, non-movement industry thinking hard. And I'm going to tell you a last thing. If you can't beat them, join them. Learn the technology now. Thank you.